Hello and welcome. In this video, we're going to go over two math problems in astronomy. One is about apparent brightness and how that relates to intensity. In other words, taking a unit or in a quantity that has defined units and turning it into a dimensionless quantity that's going to fit on a scale, almost like a ratio, but a logarithmic ratio, which is a big idea in science. But getting ahead of myself, the other problem is about comparing velocities that are very important for understanding planetary atmospheres. Okay, so those are the two topics, and let's dive into them. So the first one is considering what do planets see in terms of the brightness of the sun? How bright is the sun at different planets? So in part one, or question one, part A, you are asked not about that logarithmic scale I just mentioned, but instead just about calculating intensity. So we're asked relative to the Earth, where the intensity of light is, and here is our intensity of light at Earth. We'll call that I naught, you'll see why. And that's going to be 1,300, intensity at Earth, watts per square meter. These are always the units of intensity. Again, intensity is a united quantity, okay? That's going to be different than the value that we're just about to talk about, which has the somewhat vague name of apparent magnitude. But I just think of that as apparent brightness, okay? And that's going to be these values here, M1 and M2, okay? All right, so let's then go ahead and then consider something that isn't, like I said, the logarithm at all, but instead is a basic idea about intensities. And you may recall, it's that intensity is inversely proportional to the square of distance. So if I double the distance to something, then I decrease the intensity by a factor of 4. It's 1/4 the intensity, because I squared the 2 in the denominator. So let's see what the consequences of that are with these Jovian planets. Because we're told to find the actual distances to the Jovian planets. So you're going to need to look up the distances, and you want to look them up in astronomical units. So find distances from the sun to each Jovian planet in units of AU. And the reason that's convenient is because then you'll have this nice relationship where you can say, okay, well, I know that the Earth has the following value. That was the 1,300 watts per square meter. And I want then to compare that to some new intensity. Well, I know the relationship between intensity and distance is the inverse of the square of the distance. So over here, I would just put a 1 squared. So it'd be 1 AU and squared. Okay, now I want the ratio of that Earth intensity to some other more distant intensity, how much light, how much wattage, so the energy per time, which is the watts, per area, how much of that light energy reaches a more distant planet. And that more distant planet will be represented with a I for its intensity. All right, it won't have that subscript of 0 because it's not the baseline, it's not the comparison. And up here will be the new distance in AU. So this would be a distance, which I'll just put as the letter D, and the units of it would be in AU. The reason you want to have the units in AU is because they'll cancel out. And don't forget that it has to be squared. Now you might be thinking, well, isn't it an inverse squared relationship? Why is it in the numerator? Because it's just relative to the ratio, because of course this is effectively 1 over relative to I, right? So we have this cross of inverse square relationships. And the AUs cancel out. So as long as you looked up the distances to those Jovian planets in astronomical units, you don't ever have to worry about the more cumbersome values of kilometers, for example, because whatever you have will cancel out. So as long as it's the same unit of distance, then you'll have a nice ratio of intensities, and then you're going to solve through cross multiplication for this value. And those are going to be the 4 values that you report in part A. So you're going to have one of those values for each of the Jovian planets. So you'll have one for Jupiter, another for Saturn, another for Uranus, and a last one for Neptune. And each one should be smaller because each planet, Jupiter, Saturn, Uranus, and Neptune, get progressively further from the sun. So we should expect their intensities to fall off, and they'll fall off in a non-linear way, which is to say quickly. Okay, so that's it for part A, but we're going to think more about intensities and how we measure them in part B. Okay, so this is where things get a little bit more complicated. This is the most complicated part of both homework problems because you'll see homework problem 2 is fairly straightforward. So let's see though. Brightness, which is also called intensity. So we have a lot of terms for the same thing. Intensity is a more general term that is cross disciplines, whereas brightness is specific to astronomy. So brightness, in other words, intensity, the value I'll be using as I, can be converted to a logarithmic scale with the following formula. Now here I went ahead and actually used B for brightness, but don't be confused because it is the same variable. I'm just acknowledging that both letters are used. I'm using I because I'm certainly in the habit of doing that, but here and in most astronomy textbooks, you're going to see B. So let's go ahead and write down that B for brightness is the same, the same exact thing as I, right, for intensity, right? So the same thing. And so we could go ahead and actually rewrite this formula with an I2 over an I1, which I'll do in just a second, okay? So what's going on with this logarithmic scale? Well, the way that logarithms work in general is that, in this real general sense, is that we have division within the logarithm is subtraction outside. And that mathematical idea is represented in a way in this formula itself. So let's see on what's going on the left-hand side. Well, M2 minus M1. Here I have, let's see, so I have M1 minus M2 is the difference between the magnitudes. Let's see, so I have the 2 should be on both the tops. Yeah. Oh, that's interesting. Yeah. So I switched the order in the body of the text here. It still should say 2 and 1 because it is still that same relationship between yes. Yep. Interesting. So it should be the 2 in the front in both cases. But as the formula is still absolutely correct. All right. It's just, I'm referring to the difference here and in the wrong way, a way that would give me an extra negative. Okay. But anyway, so the difference between the apparent magnitudes of the two objects in the sky and then that ratio, that division, B2 over B1, is the ratio of those objects' intensities. Those are the ones with the actual units of watts per square meters. The apparent magnitudes, M2 and M1, they have no units. They're dimensionless quantities. They're just a number on a scale. In the same way that we have decibels with sound, that's a dimensionless quality, or maybe even more well known, the Richter scale of earthquakes. That's not measured in energy or any particular physical unit. Instead, it's just a scale. Okay, same idea here. I know I keep stressing that point. So using this formula and information from the figure below, what is the intensity of the moon as seen from Earth? And give your answer in watts per square meter. Okay, so here we're just going to kind of test out how to use this formula. So let's go ahead and put in M2 minus M1. All right, and then we have a negative 2.5 that just comes out of the way that the scale is represented, the particular spread of these values. Okay, and then we'll go ahead and put the log and squeeze it in over here. And here is the actual division, and I'll be using the letters that I used up above in part A, which will be I2 and I1. Just like so. All right, again, I and B, interchangeable terms. Now, in this case, we are going to use values of M2 and M1. So let's take a look at that, because it's an interesting scale, a good one once you get used to it, but at first it has some strange numbers, because the brightest objects, those that are delivering the most energy per time per area, so the greatest intensity, have the smallest value in the sense of the most negative value of, well, apparent brightness, right? Apparent magnitude. So the sun, the brightest thing in the sky, has an apparent magnitude of about negative 27. The full moon, the second brightest thing that's ever in the sky, has an apparent magnitude of negative 12.5 because it's basically exactly halfway between negative 15 and negative 10. As we go up, we have the brightest stars such as Sirius and even Alpha Centauri, kind of right there at an apparent magnitude of 0, right? What does that mean? Well, these are the brightest stars that are in the sky. They're the only ones that are so bright that their apparent magnitudes have a negative value in the case of Sirius or a near 0 value in the case of Alpha Centauri. Because remember, the more negative, the brighter the object. Then as we get into fainter and fainter objects, which are still relatively bright, quite noticeable in the night sky, such as the star Polaris, well, we get into things that are dimmer and harder to see. So then you get up to the faintest object visible with binoculars, or even earlier than that, the faintest object visible with the unaided eye. So notice the difference, right? You can see something that has a apparent magnitude of 6 with the unaided eye, but if you're using binoculars, you can see something up to an apparent magnitude of 10. So the higher the apparent magnitude in positive values, the dimmer and harder it is to see, all the way up to the limit of the best telescopes at an apparent magnitude of about 30, because that object is so faint, it's delivering so little actual power per area intensity that it's very hard to detect. Okay, so that's the scale, and the reason we use this logarithmic scale, right? Why do we even have this? Is because the values vary by such a vast amount. The difference between the intensity of the dimmest stars and the sun is trillions of times. So this actually is a convenience in terms of graphical representation, or in this case, kind of a number line. Okay, that's really the purpose of a scale like this. So we're going to go ahead and solve for the apparent magnitude, or rather, the intensity of the full moon based on the apparent magnitude, right? Just as an illustration of how to use this formula. I won't go ahead through all the steps because you need to do it yourself. Okay, so what do we know? Well, we know both M2 and M1 in this case because we're reading them off the table. So we'd read negative 12 for the moon. See, that's its apparent magnitude, negative 12. And then we're going to go ahead and put in the negative 27. I said 12.5, by the way. We'll have the negative 27 for the sun, but it's minus a negative. Make sure to pay attention to that. Okay, so 2, it's good to label these, is the moon, and 1 is the sun. All right, there we go. Excellent, and it's 2 minus 1. 2 minus 1, yep. You can see I obviously always forget that, even to the point of having that little typo there, all right? Because that should say 2 minus 1, just so it's the same as the formula. Okay, and then on the other side of the equation, which I'll write down on a slightly, the next line, right? But so far all I've written is just the M2 minus M1. Okay, so then we'll go write the negative 2.5, just a constant that's along for the ride, and then the logarithm. Okay, now I need to be able to find these intensities, and you can see I'm supposed to use the information about the sun. All right, so using this formula and the information from the figure below, what is the intensity of the moon as seen from Earth? And I guess I could be a little bit more clear with that, but definitely I've already given you one intensity only, the intensity of the sun as seen from Earth. Okay, so I'm in a place now where I can plug that number in. And we know that 1 is the sun, so I'm going to put the intensity of the sun down below with its 1300 watts per square meter, and then I'm actually going to solve for the intensity of the moon up top. This is the more difficult thing to do because you are solving for the value that's inside the logarithm. It's easier when you just plug it into the logarithm, which you're going to do in part C. But I guess I asked the harder one first in part B because I wanted to start with something closer to home, think about what things we're seeing at Earth, and it's a good way to understand the concept of this logarithmic scale called the apparent magnitude. But regardless, we just need to solve for it. So what you would do is you would bring these values together here. So you just combine your numbers on the left-hand side of the equation. You'd want to divide both sides by negative 2.5, okay, which is going to give you because let's see, you're going to have a positive number once you do negative minus a minus, because this will become a plus. So you essentially have negative 12.5 plus 27. But when you divide by negative 2.5, we'll make it negative again. But importantly, then you're going to raise it to the power of 10, okay? So, for example, if I don't want to use your numbers, but let's say I wanted to compare between the sun and something else. Because I probably should plug in some values. Let's compare between Venus, all right? So Venus has negative 4, so we'll put that in instead. So for Venus, M2 would be negative 4. Again, I'm just reading that off the table. This is just below negative 5, or just closer to 0 than negative 5. And I'm still going to have the sun at negative 27, okay? So then the next step here in the solution would be negative 4 minus negative 27, which would just become positive 23. And I'm going to simultaneously divide by negative 2.5 so that everything that's left on the right-hand side of the equation is just the log. Okay, still comparing to the sun, so we still have the 1300 watts per square meter in the denominator. I2 now is just going to represent the actual watts per square meter of Venus. Okay, so it's cool because it's a way, if you do know the energy of one source, you can use, and you know the distances to both of them, then you can use this information to, you don't know the distances, but if you can observe them directly in the sky, right, and actually measure the relative amount of, how bright they are, then you can calculate their energy output, okay, which is their intensity. All right, so now I'm just going to raise both sides to the power of 10. But yeah, you don't know distances in this case. There's no mention of distances. Although we, of course, do know the distance to Venus through radar and other methods. All right, so 23 divided by 2.5. I brought the negative out in front. Notice that this is all in the exponent of 10 because I'm raising everything to the power of 10. So as long as you do the same thing to both sides of the equation, you are not breaking any math rules, and we're in good shape here with our formula, okay? Now, 10 to the power of something that has a log in the exponent, well, that undoes the log. It's the inverse function. So what we're going to be left with then is just 10 to the power of negative 23 over 2.5, all right, equals I2 times the intensity of the sun, 1,300 watts per square meter. Okay, now we want to get I2 by itself, so just multiply both sides by the 1,300. And then we're going to get a final value, which says that the actual intensity of Venus, based on its apparent magnitude in the sky, is the intensity of the sun, 1,300 watts per square meter, multiplied by that 10 raised to the power of negative 23 over 2.5, which I'm going to put down as a decimal now. So let's see, 23 divided by 2.5. Remember, there's a negative. It's negative 9.2. Okay, so then let's see. All right, raising 10 to the power of 9 makes a really big difference, obviously. So what we're going to get then is 1,300 times 10 to the negative 9.2. Okay, so it will be 8.2 times 10 to the negative 7 watts per square meter. Okay, whoa, that's a really small number, right? Compared to the 1,300. Well, that's because Venus is not very bright compared to the sun, right? The sun is incredibly bright. You know, you can power solar panels. You certainly can't do that with Venus. Venus is just a faint dot in the sky. Sure, you can see it at night, but you certainly can't see it during the day when the sun is so much brighter. In other words, the sun is about 8 million times, or 80, excuse me, because it's 10 to the 7, right? 80 million times brighter than the sun. Okay, or I think I said the sun is brighter than the sun. The sun is 80 million times brighter than Venus. This 10 to the 7 factor, tells us that's because 10 to the negative 7 is 1/10 millionth. Or in other words, Venus is 1/10 millionth or 8/10 millionths as bright as the sun. But see, that's a huge difference, almost a hard number to think about, a factor of 10 million, hence the utility of the logarithmic scale. All right, the fact that we can say, oh, parent magnitude, negative 27, parent magnitude of Venus, negative 4. Those numbers are much easier to work with, okay? And it's all just as valid. We're just using logarithms to make our lives easier, but here we're getting some upfront practice with them, okay? Now, as far as the rest of this problem, I know we've been going on about it for a while. It's just more of the same. If you take a look at part C, it says, what is the apparent magnitude of the sun as seen from Uranus? So in this case, all you want to do is find the intensity of the sun, okay, which you already know from part A, plug both intensities into the formula, and then just solve for M2. Let me show you what I mean, all right? It's the last thing I'll say about this problem, because you're going to do the same thing in part D, all right? I'll at least point it out, but I won't write any more about the solution for part D. So in this case, again, we'd start the same in part C as we did before. We're just not going to have to be worrying about raising anything to the power of 10. So we'd have M2 minus M1 equals negative 2.5 times log of I2 over I1. Okay, in this case, you know both I2 and I1. I2 is going to be the intensity of the sun at Uranus. Okay, so it's what we called IU up there. All right, so that would be IU from A. Okay, so value already calculated with that inverse square relationship between distance and intensity. Okay, in that case, you did know distances, you would have looked them up. And you obviously know I1 because it's just the intensity of the sun. Okay, you also know M1. M1 is the number you read off of the figure, which is negative 27, the apparent magnitude of the sun. No units there. And you just solve for M2. All right, so you just solve for it directly. It's, as I said, much nicer than having to actually, solve for something inside the logarithm. You're literally just going to add M1 to both sides and plug everything in. So you're going to have M2, equals M1. Let's see. So we have, because it's negative M1, so it'll just be, because if you add positive M1 to both sides, and it cancels on the left, and we just have M1 minus 2.5 times log of the ratio. of intensities. Okay, so that's it for C. And I'm 90% sure D is the same. How far from the sun would you need to be for the apparent magnitude of the sun to be the same as the apparent magnitude of the moon as seen from Earth? Well, in this one, there's a bit more going on here. You're going to plug in both the apparent magnitudes. You're going to be able to then calculate the intensity, and you're sort of actually fitting together some of these ideas because you will eventually have to solve for distance, because in this case, you will have to solve for intensity. You're going to solve for a new intensity, an intensity that matches that of the moon. Although if you think about it, you already know that from part C. And then once you have that new intensity, then you have to go back to what you did in part A, but backwards, and solve for a distance rather than knowing a distance. Okay? So kind of a really interesting idea. And honestly, it's a very interesting question, right? Because the sun is still quite bright, right? Even when you're very far from the sun, way out in the distant solar system, where the angular size of the sun isn't much bigger than what we're used to as stars, it's still much, much brighter, hundreds of thousands of times brighter than what we think of as stars. So it'd be a very different object in the sky, one we're not used to. So like a dark sky, but a very single bright spot. And so the idea then is that how far do you have to be until it really becomes faint enough to be as faint as the moon? So enough about intensities and light and how we observe it. Let's talk briefly about question 2, only briefly because it's a pretty straightforward calculation at least, all right? So the idea here is that there are 2 important velocities for the building and keeping of an atmosphere of a planet, okay? So we have the idea that there is escape velocity. This is the same concept that applies to rockets. If a rocket is going fast enough, it's able to gravitationally escape a planet, okay? It will move away with enough kinetic energy that it's able to overcome the negative potential energy it had on that planet. It gets away from the planet, okay? You can also have enough velocity to get away from a star and permanently leave the solar system, okay? Furthermore, there's a velocity that's called the thermal velocity. That's this one here. And the thermal velocity relates to basically the motion of tiny particles in a gas. The fact that if you zoom in on the submicroscopic scale to a gas, you see lots of little atoms or molecules bouncing around. Well, they have a certain average velocity. Of course, there's trillions upon trillions of them, and some of them are not moving very quickly at any given instant, but others are because they got ricocheted off in a certain way and they're moving quite quickly. And this principle applies to gases in that it tells you, the likelihood of what velocity they're going to have. And in an open container, effectively like an atmosphere, very fast atoms and molecules in that atmosphere, well, they might just be moving fast enough to gravitationally escape the planet, right? Just by chance, just because of the thermal energy that's making them bounce around. Thermal energy just being heat, all right? So the hotter the planet, the more likely it is that they're able to lose certain atoms, but it also depends on the mass of the atom. Because you see here that M actually shows up. So different gases have different likelihoods of escaping because they'll have different thermal velocities, and those thermal velocities may or may not be greater than the escape velocity. Because you better believe it, if the thermal velocity is greater than the escape velocity, then that type of atom or molecule will not stay in the atmosphere of the planet over a long time. Because over time, those faster molecules will just happen to occur, and they'll escape into space, and they'll never come back, okay? So the principle here, let's look at the question, is what is the escape velocity from this altitude? And what's this altitude? Well, you're working with the planet Titan. No, not planet. The moon Titan. It's a moon of Saturn. And we're talking about its very upper atmosphere in order to get some dramatic numbers. So we're considering a point that is 1,000 kilometers above its surface, which is quite dramatic because the whole planet has a radius of only 2,500 kilometers. So we're almost, we're more than half a radius above the surface of the planet. So really, on the far edge of what you could possibly consider an atmosphere. And here we're given the mass, I said planet again, excuse me, moon. And here we're also given the mass of the moon, all right, which it's a very large moon, all right, not as large as Earth, but still, as moons go, very large. What is the escape velocity from this altitude, all right? And you're just gonna plug the values into the formula. So here let's collect our values for part A real fast, so you are good to get started on this. So big G is the gravitational constant, which you've been seeing a bit of, 6.67 times 10 to the negative 11 kilogram meters squared per Newton squared. All right, M is the mass of the planet. All right, so in this case, M is just the 1.346 times 10 to the 23 kilograms. All right, that's the M in the formula, right up here. And then let's look at the denominator. Well, in the denominator, we have the radius of the planet. All right, so this is, now the thing is you can't leave it in kilometers, okay? So we have to convert that value into meters. In this particular formula, basically any formula that has big G in it or other universal constants, you always have to convert to base units, and kilometers are not base units. So we need the radius of Titan, we'll put a T for Titan, in meters, all right? So we have 2,575 kilometers, but you must convert, which I'll leave up to you, all right? So convert to meters. Okay, and the last thing is the altitude, which is the plus h, all in the denominator inside of the square root, and h is 1,000, but again, it's in kilometers, so you also must convert. You don't have to convert anything else. Obviously, the gravitational constant is base units, and the mass is already given in base units of kilograms. Okay, and I know why are kilograms base units but not kilometers? Just the way it was decided, but also convert to meters. Okay, but we have to all agree on the same base units. Okay, so once you plug that all in, you can just simply plug it into the formula and get your value for part A. Okay, so plug in directly, report the value in meters per second. Okay, so your final V for escape in meters per second. Okay, so that's it for A. For B, we're then told the temperature in the exosphere is 200 Kelvin, so cold, but not incredibly cold as far as space goes, but still, the 130 degrees Celsius colder than it is here, or 170 degrees. 100 degrees Celsius colder than it is here. So well into the negatives of Fahrenheit. Then what is the thermal speed of hydrogen in Titan's exosphere? All right, and we're going to use the formula that we're given for the thermal speed, that idea of the likelihood of molecules bouncing around and picking up a certain velocity. All right, and it's kind of like the average velocity. K is a given constant called the Boltzmann constant. You can see it's 1.38 times 10 to the negative 23. That's this value right here. Okay, so kind of like G, it's a universal constant. So again, think base units. And then, although here everything is given in base units. And then M is the mass of the atom that we're interested in, which was, let's see, I guess it's hydrogen, okay? Yeah, the mass of hydrogen, okay? So you're simply going to find the thermal speed of hydrogen. You'll plug in that value of M, and then plug in the value of T. No conversions here, so I won't write down the values this time because there's just a few of them. But you'll plug in this value of T, all right there. It's already in the correct units. Leave in Kelvin. Plug in your constant. Make sure to include that large negative exponent there, all right? So it's a very small number. There's a 2 inside the square root, so they're both square root formulas. And then here, you're not dividing by radius or distance or anything. Your value in your denominator is just the mass of hydrogen, which is already there in kilograms. And remember, it is also a very small mass because we're talking about a single hydrogen atom. Okay, so then you have your 2 velocities. That's all you report in part A and B. And then in C, it's the fraction, all right? So then what fraction of the exospheric escape speed, that's the value that you solve for at A, is achieved by a typical hydrogen atom at thermal speed in the upper atmosphere, okay? So in other words, since we didn't really write anything down for B, I'll erase that and write C, all you need to report for C is just V thermal over V escape. Okay, I think that's the way I asked it, because it said what fraction of the atmospheric escape speed is achieved by a typical hydrogen. Yep, because the achievement is the thermal speed, right? So that's your typical velocity, just because it's hydrogen at the temperature. And then how close is that? What fraction is that value of the necessary escape speed? Because in other words, if that ratio is close to 1, then we would expect most of the hydrogen to escape very easily, right? On the other hand, if the value is really small, like a tiny value, right, like 1 over 1,000 or something, then it would be incredibly unlikely for any hydrogen to escape, and we'd expect this atmosphere to retain hydrogen. Okay, and hydrogen is often the most interesting because it is the smallest atom out there, so it's the most likely to escape if the conditions are right. And the conditions are right whenever the temperature is high enough, or the planet is small enough, or the altitude is high enough. Okay, so hopefully that approach to 2, which you can see is straightforward on a calculation point of view, just mostly what you call plug and chug, but hopefully the concept and the approach makes sense. Well, thank you so much for watching this homework help video. I hope my tips and comments have been helpful. See you next time.